Welcome to part 2 of our workshop on EXAFS shell fitting for environmental samples. This video accompanies part 1, and the goal of this video is to illustrate how to use Artemis for shell fitting of EXAFS data. And what I'm going to outline here in more detail than that presented in part 1 is a type of protocol you can use to get you set up and running your fits. So here I have an outline of the protocol that you can use to get you going on your fits. This video is mostly going to focus on Artemis, but I will show examples of Athena and background subtraction. So let's get started. The first example we'll be working with is the nickel foil. So we're going to load the nickel foil into Athena and do background subtraction on that. Select our nickel foil and open it. You may have to change some of these options depending on your data set. I can select the default for these data. Here are raw data. The first thing we'll do is select pre and post edge normalization lines. So let's plot those using these boxes here. And the defaults are fairly good. I'm going to modify them a little bit just to ensure we're on the data and not on any of the curved portion of the pre-edge. I want to expand this plotting range so I can see everything. Going to select post edge normalization range to get the line to go pretty much through the oscillations, right through the middle straight line and essentially parallel to the pre-edge normalization line. And plot those data now. We're going to use a k-weight of 3 for these samples. This sample, there are reasons to plot and fit in k-weight of 2 and 1 and 1, 2, and 3 simultaneously. But here we're just going to use 3. Let's look to see our spline. Make sure that we're on the end of the data. All right. Those are our background subtracted data. The next thing you want to do is File, Save Project, and you can open that project file in Artemis. I already have a project file that I want to use, so I'm not saving it. Next I'll go to Artemis. Alright, pick R range, K range, and sills. I'll show that in Artemis. Open our project. This is the project I'm going to use. It's the same data that I was working on before, just with specific background parameters that I want to keep the same from my fitting examples. So we're going to import that. There's just one spectrum in that file. All right. R and K ranges and sills. So we're looking at our window. Our K range right now is from 2.5 to 12.5 here to here. You can adjust that. Our range that we're looking at is 1.7 to 2.7, so we're focused on the first shell. If we do a back Fourier transform of this R range, we can see the contribution of the first shell to the EXAFS data, and we can plot those data on top of the EXAFS data and see we're generally following our large oscillations. However, we're missing a lot of these shoulder features. So if you want to see the effects of how these shoulder features appear in the data, you can just expand your R range. So if I expand it out to, say, 5.5, click R again, you can see the R range expands. Plot the back Fourier transform of those data, and now you can see we're starting to show a lot of those shoulder features that are present in the raw data. Still, we're not capturing all these smaller features that are results from multiple scattering from the nickel foil. And if you wanted to capture those, of course we're going out really far in our space here. We're not going to fit all the way out here, but this is just to illustrate what happens when you do include more of your R range in your back Fourier transform. Then we can start to see we're capturing some of these shoulder peaks a little bit better. But in general, EXAFS is only sensitive out to about 5 angstroms, and we're doing a back Fourier transform out to 8. This sample is highly crystalline. Nickel foil has a cubic crystal structure, so there's a lot of linear multiple scattering paths and a lot of numerous degenerate multiple scattering paths. So you do see some contribution from multiple scattering at very high R range, but we're not going to fit those data out that far. So let's get started. Our DR and DK. So DK and DR is the slope of the sill. This is the sill here. It's the part of the window where the window goes from 0 all the way up to the maximum. And you can change that slope in K and R. So here I'm using a DK of 1 if I wanted to make it higher, just to show you what the effects are. You can see how that changes the slope. I usually use a DK of 1 and a DR of 0.5. If you were to make that bigger, the same thing happens. You change the slope of it. But I usually use 0.5. So now we're going to go ahead and start fitting. All right, we're going to use K weight of 3 on these data. And for the first part, we're going to load the pass for the first shell and set the parameters. Okay, so let's go back to our protocol. Load data into Athena, do background subtraction, save file. We did that. Open Artemis, load data either from Athena or as K-weighted EXAFS data You set your R range, K range. Changing these values also changes the number of independent points, which will be important when we're considering how many variables we use in our fit. Check your sills. Load our CIF file into Artemis. So what is a CIF file? It's a crystal information file, and we usually use those as our structural model base for the software program Atoms to build a cluster, which is our structure model that we'll use to fit our EXAFS data. So I'm going to look for, using the American Mineralogist Crystal Structure Database, nickel, and search for elemental nickel. I already know which one I want to use. It's this one, which is at 293K. You can see the second sample is at 578K, so you need to pay attention to the notes in each of these and scroll through multiple ones to find the one that's most appropriate for your samples. I've already downloaded this, so I'm going to go ahead and add it. This is my CIF file. When you name the CIF file, try and keep the name relatively short. Okay. Here, Atoms and FEFF have opened up, which are inside Artemis. All right, choose an appropriate structural model for your data. Pick a CIF file from which Atoms will make a cluster. Check for partial occupancy and modify the CIF file if necessary. We don't have any partial occupancy in this CIF file, so we don't need to do that. We need to set our cluster size to 9 angstroms and our longest path to 6. Those are the defaults I usually use. You need to make sure your cluster size is bigger than your longest path. This ensures that all the atoms used to calculate scattering paths are well bounded, meaning they have atoms on the outer side of them as well. We don't need to go any further than 6 angstroms because generally EXAFS is insensitive to scattering beyond 5 or 6 angstroms depending on multiple scattering. But that's generally as far as you need to go. The next step, check if the absorbing atom is selected, has the correct label. It does. Add, swap, delete atoms if necessary. That's actually in the next step. So we're going to go ahead and run atoms. You can check your IPOT list. We just have nickel in this, and here's the atom list going out to 9 angstroms. Then we'll go and run FEFF, which will calculate our scattering paths, which we're going to use to fit our data. There are scattering paths. So, load CIF into Artemis, run atoms, run FEFF. Select our range that we're going to use for the first shell. We're going to fit the first shell and work our way out to higher shells or higher in R space, and then repeat steps as necessary. Select the range just to encompass the first shell. I usually round up or down to the nearest 0.1 angstrom depending on the location of the shell. So for this first shell, I'm going to select 1.7 to 2.7. Okay. So at the bottom end of that shell, I rounded down to 1.7, and the top end of the shell I rounded up to 2.7. The next step is select paths from the FEFF calculation dialog box and drag and drop them. So we're going to select paths that have have significant contribution or high ranking and are located at appropriate distances to the center of the peak. Remember to account for phase shift, which is generally minus 0.2 to minus 0.5 angstroms. So when we look at our scattering paths, the center of our peak is about 2.2 angstroms. The first scattering path listed is at 2.5. So our real data are about 0.3 angstroms shifted by the phase shift. If we look at our ranking, this is our most significant scattering path. So we're going to drag and drop it into our path list. Next, we need to label all the variables selected for the selected paths and transfer them to the guess def set list using math expressions as appropriate. So what that means is, of those 5 variables that we fit, which are part of the EXAFS equation, those variables are listed here. Each path needs to have those variables assigned. 1, 2, 3, 4, 5. These are the ones that we're generally going to fit, these 5 variables. So because we know what this sample is, we're going to leave the coordination number as 12 because we know it. I know it's a nickel foil. That's that's the sample that it was collected on. The amplitude reduction factor I'm going to label as amp. The change in energy I'm going to label as E naught. The change in R I'm going to call delta R nickel 1. Nickel 1 because that's the path nickel 1. Sigma squared nickel 1. So now we have those 5 variables assigned, and we can actually determine our amplitude reduction factor because we know the coordination number. So this is one way to determine your amplitude reduction factor for other samples run at the same time on the same beam line during the same beam trip at the same elemental edge. So other samples run at the nickel K edge. You could use this to determine the amplitude reduction factor for your other samples run at the nickel K edge. It's called chemical transferability. Or this number is chemically transferable to other samples of the same element. Okay. So we need to transfer these variables to our guess def set list, which pops up here. All of these windows you can toggle on and off. I recommend looking at Bruce Ravel's videos on EXAFS education, which explain very well what all the windows do. So you can right-click in here and transfer these variables up to your guess def set list, which is going to contain all of the variables for all of your scattering paths that you select to fit the data. So we have labeled our variables for the selected paths, and transferred them to the guessdef set list. Now we can go ahead and click Fit. Here are fitting results. Our number of independent points, our number of variables, chi-square, reduced chi-square, and R factor. It's a very low R factor. Amplitude 0.84 is a reasonable value with a reasonable error. So that's our amplitude reduction factor. E0 is kind of high at 6.5. We can go back to Athena and adjust the E0 value that we selected, the E0 value that we selected in Athena, and import those data again back into Artemis. We can adjust E0 to line up more properly with the data. This value should be between 2 and 3 electron volts. It doesn't create any problems here for this fit, so I'm not going to change it or illustrate how to do that, but I talk about that in the previous presentation. Delta R is small, sigma squared is reasonable. So you want to go through each of these values and ensure that they're reasonable. And the previous presentation discusses what those reasonable values are. The happiness factor does go through and checks some of these, but you need to do it yourself. So I'm happy with the fit of this first shell. You can see in magnitude and in real, the magnitude and the real part of the Fourier transform are good in terms of magnitude and phase. So I'm going to go ahead and select, that's my fix. So we're not going to fix E0. All right, we're going to select the path for the second shell now. We reviewed the results. All the values are physically reasonable except E0. That's a little bit high, but we're not going to worry about it for right now because I've done this fit and it doesn't create any problems. Constrain the fit. Remove variables that overlap using the methods discussed in part 1 of this workshop. So we don't have any variables that can be removed. We're only using 4 because we're using the first shell and we need to guess them all. So we're not going to run the Hamilton test on this fit. So let's go back to our data. Whoops. And look at our second shell, which comes up at about 3.3 angstroms. So with the phase shift, we're looking for a scattering path that's somewhere around 3.0 to 3.1. Oh, sorry. No, we're going to add 0.2 to 0.5. So it's 3.5 to 3.8. Here's our next significant scatter at 3.5 with a degeneracy of 6, meaning 6 equal scattering paths. I'm going to drag and drop that. And we're just going to follow the protocol, repeating steps 4 through 10 as necessary. Well, we already did 4 and 5, so now we're just going to repeat steps 6 through 10. As necessary. So we're going to move up in our R range. We did that. Actually, we haven't assigned that R range yet. So we want to use, I think, what am I using? 3.6. 3.6. You can click on R and see the R range moves out. We moved our scattering path over. We need to assign these variables, amplitude, which is shared between all the scattering paths, E naught, which is shared between all the scattering paths, and usually delta R and sigma squared, I usually give them their own, initially their own independent variable. Those are generally the ones that tend to differ between paths, but they can also overlap and be restricted significantly. So we'll call this one delta R Ni2 because this is Ni2, second path, second shell. Sigma squared Ni2, and we'll transfer you guys up to our guest def set list. And so we selected our path, we labeled the variables. We're going to click the fit button. I'm going to open up my history window. I generally like looking at this because I can toggle between fits very rapidly. And amplitude reduction factor looks good, the same as before. E naught still big. Change in the first shell is small in terms of delta R. Sigma squared is reasonable. The error is reasonable. Delta R for the second path is reasonably small, as is sigma squared. Happiness isn't picking up any significant correlations between above 0.95. So the statistics look good on this second shell fit. You can see there is some misfit in terms of magnitude, and phase looks pretty good. But that's going to improve as we add more shells to the fit, more paths to the fit. So we're going to go ahead and fit the third shell now, moving out to about 4.3. angstroms. So change your R range, select a path, assign the variables, fit. That's kind of the protocol. Select your R range, select the paths, label your variables, fit. Then you review the fit and constrain it if possible. So our next scattering path should be around 4 plus the phase shift. So 4 plus 0.3 is around 4.3, and that's where we see our next shell coming in with a high rank, and it's a single scattering path. So the paths that generally contribute most to the EXAFS are single scattering. Multiple scattering, especially in highly crystalline samples, play significant roles as well. Here I'm just going to focus this next path will be a single scattering path. And so I need to label amplitude E naught. So all these paths are going to share amplitude and E naught. They use the same value. When Artemis goes through to fit the data, using the EXAFS equation for each path, it's going to the guest def set list, and it's going to grab those parameters from there and use them to fit each path. So we're telling it to use the same value for each of those paths. Delta R, nickel 3, sigma square, nickel 3. We need to transfer these up to our guest def set, and we'll go ahead and fit. Visually it looks good. Let's look at the statistics. R factor is pretty low. sigma squared here and sigma squared here are overlapping in terms of their error. So that might be something we can constrain to have them share the same value because they're both the same atom and they're both in higher order shells. So I'm happy with that fit. And I'm going to go ahead now and select the path for the fourth shell. Fourth shell lies at about 4.6 angstroms and ends here around 5.1. So we're going to go out to 5.1. And we're going to select our next path. So 5.1 plus the phase shift of 0.3 to 0.5 is about 4.65 plus 0.3. So something around 4.95 to 5. And we're seeing actually many paths, many multiple scattering paths, and a single scattering path at that exact range. So I'm just going to pick this single scattering path. Generally those contribute significantly to the EXAFS data. We can look down here and see this high degeneracy of 24, and these has a ranking of 48, and this at the same R range, same distance, has a degeneracy of 12. So there are many different scattering paths in this highly crystalline sample, many different multiple scattering paths that also look like they contribute significantly to the oscillations. So, but we'll go ahead and we'll pick the first one here, the first single scattering path. Assign our values, amp, E0, del R, nickel 4, sigma squared, nickel 4. Guess. Okay, and fit. Alright, it's not liking the fit. History. R factor is high. It's giving me penalty because of high R factor, and saying delta R for this last path I put in is suspiciously large. So one of the nice things about the happiness factor is it does go through and pick up something like this. The delta R higher of 0.1 generally means there's something wrong with the model you're using. Here you can see the path. It's getting pushed all the way out of our fitting range, so it doesn't like it. It doesn't like this scattering path. And the reason why it didn't like it is because I haven't been using the best fitting parameters, the best guessed fitting parameters for each fit. So what we're going to do is click on our guessed def set list, and every time the fit is evaluated you get the results here. And if you don't click use best fit to transfer your initial guess into the math expression column, it's going to use the value that was there to start with. But we want to start at the best guessed initial fit. I'm going to change that back to 0 so that it's not guessing that the path is already moved out by 1 angstrom, 1.1 angstrom. So I'm going to put it initially guessed back where it should be. I'm going to go ahead and run the fit again. And we can see here fit 5. Now it likes the fit more. Our R factor has gone down. We're still getting a penalty. Anything above 0.02 I think gets a penalty here. And if we look at the magnitude of the fit, you can see that we're not quite there yet. We are missing some data. And at the phase looks pretty good, except in this part here, we're a little bit out of phase. So we are missing something in phase and magnitude. Our delta R for that path is pretty big. I think what we need to do is go back and reconsider some of these multiple scattering paths. This is the next largest contributor, path 11. So I'm going to go in and bring that, drag it into the fit. Okay, again, we're going to click use best and label these amplitude, guess, fit. So now it seems like the fit is good. We can see that last shell in terms of magnitude were much better visually and in phase. A little bit out of phase here, but this is at the very end of the fourth shell. So we're doing real well for fitting out 4 shells in pretty high R space. Our delta R for that path is still pretty big. So I labeled this, I gave it its own sigma squared parameter. Sigma squared is kind of big, but for multiple scattering, I think it's acceptable. Delta R, sigma squared for the rest of these. What's interesting though is that several of these paths, several of these sigma squared parameters in the higher order shells are overlapping. So this one, this one, this one. When you take into account the error in this column, added plus or minus to the calculated value, they all overlap. So what we're going to do is start constraining this fit, which is one of the steps in the protocol, and see if we can remove some of these extra fitting parameters. We want to reduce them as much as possible. So yeah, that's 12. We have 12 variables now. Each time we added 2 variables for each path. So now we're up to 12 variables in our guess def set list. Delta R is still big. We want to constrain some of these variables to get them, we can get them into a little more acceptable ranges. The sigma squared for the multiple scattering path was kind of big. So what we're going to do is we're going to group paths that are overlapping. We're going to group these sigma square values. We're going to assign them to be the same thing because they're all in higher order shells and they're all scattering from the same element. So we're going to, in the guess def set list, we're going to go through these last 3 and skip them, and you can see they get grayed out as I right click and click skip. And I'm going to set them all to be the sigma square value for the second scatterer. So now all 3 higher order shells are going to use the same one. It's probably not entirely appropriate to use the same sigma square value for multiple scattering, but I'm going to assume that it's fine here, and we're going to go ahead and do the fit. So what I did was remove 3 variables from our fit So we'll go ahead, 3 variables from all of our paths. Go ahead and do the fit. And we do get a slight increase in our R factor from 0.11 to 0.12, so not a big increase. But we reduce the number of variables from 12 to 9. And that's the goal. And anytime you add a variable to your fit, your R factor generally goes down. But you don't know if it's going down significantly or not until you do a calculation to prove to yourself that. So one way you can go about doing that is using the Hamilton test. You can see by constraining our fit and adding that extra path, our delta R, which was kind of big before for the fourth shell single scattering path, actually has gone down a little bit. So what we're going to do now is just illustrate how to do the Hamilton test to see if adding those 3 extra variables, which gives us a smaller R factor, is realistically is really smaller or not, is significantly smaller or not. So to do that, we need a couple of pieces of information. We need the R factors for each fit. We got those here. The ratio of those R factors, which is 0.918, the number of independent points, the number of variables, the degrees of freedom, which is the number of independent points minus the number of variables. And for the Hamilton test, there are 3 parameters that you need: A, B, and X. A is the degrees of freedom divided by 2. B is the difference in the number of variables between the fits divided by 2. And X is the ratio of the R factors of the fit. So 21.3 minus 12 is 9.3, divided by 2 is 4.65. 12 minus 9 is 3, divided by 2 is 1.5. So we're going to go to our calculator. This is the calculator I use online. Put in our variables. 4.65. B is 1.5. And X is 0.9118. Calculate. 0.84. So what does that mean? If we're using a 95% confidence interval, anything below 0.05 or 5% indicates a statistically significant improvement in the fit. We're at 84%, so we're way above that. So in this terms, there's an 84% chance that the difference between the fits would occur by random variation or is just due to noise in the data. So that's what I'm going to call it. It's just due to random variation. It's not significantly improving our fit by adding those 3 variables, so I'm not going to include them in the fit. So the Hamilton test proves those 3 variables were not necessary to improve the fit. What I'd like to do now, we're going to keep these variables here. For our best fit here is it. And what I'd like to do now is just illustrate how to use some of the multiple scattering paths. I'm not going to save this file. Generally, you want to save it often. I've done this several times, so I'm not going to save it even when you're doing your fits. After each fit, generally, I save the file. I'm going to exit. What I'd like to do is show real quick how to So what I'm going to illustrate is how to use the multiple scattering paths in your FIT. I'm going to load the same project file I did before. Set my windows up in a way that I can generally see all 6 of them or get to them easily. Okay. Review K-way to 3. What do I want to do? I want to do full multiple scattering up to 5.1. So this is the same R range we were just using in our other FIT. I'm going to load my CIF file again, change my cluster size and my longest path, run atoms, run FEFF. Now, because this is such a highly crystalline structure, we have a lot of multiple scattering that's significantly contributes to the EXAFS oscillations. So what I'm going to do is I'm going to select paths with a rank above 8. And I'm going to Control deselect these because they're out of my fitting range. And I'm just going to drag them over here to our path list. I need to assign variables for all of these. They all share amplitude. They all share E0. And what I'm going to do here is employ an isotropic expansion contraction term using a math expression. These text fields you can add, multiply, divide. They're sensitive to math equations. And there's a special keyword in Artemis called REFF, which is R effective, which is this number here. So for every path, it's going to take the R effective and multiply it by a term. I'm calling that term alpha. And I can right-click and export this parameter to all paths. So now I can click on any of these and they all have it. I'm going to guess amplitude, guess E0, guess alpha. If you were to have 2 parameters in here, you can right click on one and that pop-up box will appear for each one. I'm going to guess alpha, which is going to be a variable that's going to get multiplied applied to each R effective for each path. So each path is going to change by the same proportion. And we can do that for highly crystalline structures like this cubic structure for nickel foil. Guess nickel 2. So there are a lot of multiple scattering paths in here and single scattering paths. And they're all going to get the same sigma squared value except the first path. That one I generally, in almost all cases, give it a specific sigma square value because it's generally different than the higher shells. There are ways to constrain sigma squared. If you go back to the other presentation, I talk about those. By not putting in any multiple scattering paths, you can also consider that a way of restraining the fit. And that can sometimes be bad because multiple scattering can be significant to your fit. So even if you're not sure how to assign a sigma square value for a multiple scattering path, it could sometimes be just a good idea to include it and assign it your best educated guess as to what it could be, not letting it be free, not guessing it, but restraining it to be either twice that of another scattering path or half that, or other ways of restraining it. So you're not adding any more free parameters, you're not adding any more variables to your fit. So there are ways of restraining this differently for multiple and single scattering paths, but for this purpose I'm just going to assign them all to be the same except for the first shell. So now actually I only have 5 variables. Amplitude, E naught, which were shared with the other fit, they were shared between all the paths. The alpha term and the sigma squared for all the other paths, and the sigma squared just for the initial, the first shell. So I'm going to go ahead and click fit and see what happens. And just looking at this R factor, it's pretty good compared to our other fit. Our amplitude is fine, 0.9. The error is fine. The E naught is big, just like it was in the other fit, and we can fix that. I'm not going to show how to do that now. The alpha term, it's only saying to change each R effective basically by 0.0008, so almost nothing. So it's saying that the structural model is exactly correct for these data. Sigma square value for all the shells and multiple scattering paths except for the first one is reasonable at 0.0089, and the first shell is also reasonable. Happiness looks fine. Our correlations are below 0.95. If you scroll down, you can see the results. Your calculated R, your delta R, all down here. You can see our delta R is small for all of these. So I'm using 5 variables. My R factor is 0.011. When I compare this fit with all the multiple scattering paths to the other fits that I did independently, which have more variables, I had 9 variables in this one. I had 12 in this one. This R factor is lower than these two. So I can't even do the Hamilton test on this because I'm using fewer free parameters. But the fit is better because I'm including those multiple scattering paths. This is an example where multiple scattering is important and to consider when you're doing the fit. Okay, we're done with this sample. We're going to move to the next one. There are 3 total that we're going to talk about here. The next sample we're going to open up in Athena. This is a beta nickel hydroxide, so you can think of it as just sheets of octahedra connected together. The octahedra connected together, the sheets are independent of each other. we're going to open it in Athena and do our background subtraction on it. And I'm going to use this sample as an example of the effects of the RBKG, the R background value. Select pre and post edge. That actually looks good here. So we can see our E naught. These data were already calibrated. You can see our E naught is actually on the white line portion, which is above the oscillations here. It's an edge feature. We're going to move it down a little bit so that it's on the rising portion of the absorption edge. People use different ways to determine E naught, but you need to have it on the rising portion of the absorption edge, not down here and not up here, not in the Zanes or EXAFS region. Okay, right click, copy data. I'm going to assign, whoops. Alright, right click, set all groups to these values. Look at the K-weighted data. Purple buttons, plot the checked ones. Our window. That looked good. You can see this large peak out here, which is a result of multiple scattering in the hydroxide sheet. So what I want to illustrate here is how to determine the best R background value. So I have a copy of the data. They have the same background subtraction parameters. What you can do is set this unreasonably low so that you're not subtracting out any low frequency oscillations in the EXAFS data. And you can see these low frequency oscillations are now present in that sample. And because these oscillations that are at a frequency lower than that of the first shell, they're not part of the EXAFS data. They're not formed from scattering paths. So we set this to an unreasonably low value, and now I'm just going to go up one by one, 0.1 by 0.1 to see when this gets reduced the most without affecting the first shell. So this is at 0.3 and this is at 0.5. I'm going to go up to 0.6 can see nothing's really changed. I'm going to go ahead and set this one to 0.6. And we'll go ahead and keep going up. 0.7. We can still remove a little bit more. 0.8. You can see we're starting to, we're continuing to go down. We're continuing to eliminate data before the first shell. 0.9. It's gone down a little bit more. 1. It's gone down a little bit more. Our first shell looks still like it's intact. What happens when we go up even more? You can see we start to get some artifacts. So I'm going to just leave it at that and say 1 is the ideal R background value for this sample. I'm going to go ahead and save this project. Alright, so following our protocol, load data into Athena, do background subtraction, save the file, open Artemis, and load data. So we're going to go ahead and do that. Open Artemis. We want that sample, not the copy, because this has the correct R background value. Check our K range and our DK. Those look good. They were exported with Artemis. I didn't change these. The R min in Athena. So I'm going to go ahead and do that. I'm just going to leave it probably at 1 to 2. 1 to 2. Even though the first shell is right up here, I can probably scooch this up, but we'll do 2.1. Okay, now I load a CIF file into Artemis. So I need to choose an appropriate structural model. I know what this sample is. It's one of the standards I use. It's a beta nickel hydroxide. So I can go to my database and search nickel nickel hydroxide, and nothing's there. This database is very sensitive to the word that you type in there. Even if it's misspelled, it won't find it. In this case, we need to search for the mineral name. So another name is theophrastite. So I'm going to copy that and search for that. Whoops. Search. Frastite. And it found it. The one I generally use, I've already downloaded these CIF files, is Ramesh. So I usually pick this one. So we're going to download it, save it. We're going to call this okay. So we got our CIF. Add. These are our atoms, nickel and oxygen. I'm going to change the cluster size to 9, longest path to 6. We're on atoms. In our iPot list, we can see we just have nickel and oxygen. We can look at the distances. The absorber is at 0. The 6 oxygens are located here at 2.08. In the second shell, we have 6 nickels, and so on. Our list goes out to 9. Run FEFF. Okay. So we ran atoms. We didn't need to change anything in it. We ran FEFF. Select R range for our first shell. We did that. Now we need to select the paths from the FEFF calculation. Our first shell is at 1.65, so 1.65 plus 0.3 to 0.5 is around 1.95 to 2.15. So we know this is the one we want, taking in the phase shift into account. It's at the right distance. Our effective is the right distance. It has a degeneracy of 6. There are 6 oxygens in the nickel octahedron structure. So we can also use this sample to calculate the amplitude reduction factor. We can leave n as 6. The coordination number is 6. We can guess the amplitude, we can guess E naught, we can guess delta R nickel, and we can guess sigma square for nickel. So we labeled the variables. We need to transfer them to the guess def set list and then fit. Okay. Looks to be a good fit in magnitude in real phase. Number of independent points, number of variables, chi-square, reduce chi-square, and R factor is really low. Our amplitude is 0.8, which is very reasonable. E naught is small. Delta R is small. Small error. Sigma squared is small. Really small. With a small error. These data were collected at liquid nitrogen temperatures, which reduces the thermal disorder. So that's why the sigma squared value is so small here. I'm then going to expand my R range to about 3.4 and fit the second shell. Click, drag. Oops. I think, yes, I used the wrong labels here. This is oxygen. And that's nickel. All right, what's the problem? Sigma squared is a guess parameter not used in the math expression. Sigma squared for nickel. All right, because I'm not labeling properly. Sigma squared, delta R oxygen, and nickel. Should be okay. All right. The fit looks good for the second shell. This is a standard. It was well characterized. I already knew what it was, so the fit is saying that the structural model agree with the data and that it actually is a nickel hydroxide, a beta nickel hydroxide. Our amplitude, reduction factor, and E naught. All our variables are within acceptable parameters. We scroll down and look at our calculated R values. They're very close to the R effective. There's very little change suggested by the fit. We left our coordination numbers fixed as 6 because this is a standard and we knew what they were. So that's a short example for how to fit the beta nickel hydroxide. Just going to quickly save this. And now we'll move to the last example. Which is nickel reacted with pyrophyllite. So the sample I'm going to show you is from this paper here from 2009. Just following our protocol, load the data to Athena, do background subtraction, save the file. These are transmission data, already calibrated. collect it up to very high energy. I'm going to go through the R background procedure again. Still removing a little bit before the first shell. Now I'm starting to create some artifacts. So again, we're going to stick with one. We loaded our data into Athena, did our background subtraction, save the file, open Artemis and load data, check the ranges. Pick the right file, which is this one. Okay, the CIF file that we want, I already have downloaded. This sample's also pretty well characterized. It's been published. And I use lizardite to fit it, which is a serpentine mineral, layered silicate mineral. And this is where I want to show some examples of doping and how to substitute atoms in and out. So I already know basically what this sample is based on several distinctive features in the EXAFS oscillation. And it's a layered hydroxide, a layered double hydroxide. It's nickel reacted with a aluminosilicate mineral pyrophyllite for 6 years, and we know secondary precipitates form called layered double hydroxides where nickel and aluminum are in a hydroxide sheet, and that's indicated by this distinctive beat pattern here. In the EXAFS data, there's a truncation here in the EXAFS data between layered double hydroxide and a hydroxide caused by the lighter element aluminum in the second shell. So in terms of getting the right atoms into my list with respect to those that are already present, I'm going to delete hydrogen. It's not important for scattering here. Our core atom is going to be nickel, so we're going to change this to nickel, and then we'll just make our cluster a little smaller. And silicon is also present in the tetrahedral sheet of this silicate mineral, so we're going to leave that there because the layered double hydroxides over time can silicate and also have silicon in there adjacent to the octahedral layer. So now I can run atoms. I also know I need aluminum as a scattering path. So when I want to add another element to my scattering path, you need to edit the FEFF input file. We're going to add another atom in the IPOT list. Aluminum is a Z of 13, and we're going to call it AL. Now I suspect aluminum is in the second shell here, and also it's present out here in multiple scattering, but we're not going to fit the multiple scattering peaks right now. So here's my first shell, oxygen, right here. Here's my second shell, nickel or magnesium, which was what the lizardite structure came with, and I substituted it for nickel. And also silicon is also very close in the second shell, only about 0.2 angstroms away, as part of the tetrahedral sheet. So this is our second shell, and you can tell by looking at it, it is a little bit smaller than the beta nickel hydroxide, and that's caused by the destructive scattering of aluminum. So I need to put aluminum in this list somewhere, and you do that by changing the IPOT value, and I want it in my second shell. So I come in and type in aluminum, and I can control copy and paste it in. I'm going to paste it in 3 times, and I'm doing it every other atom so that the degeneracy is similar between the two. Silicon I'm leaving the same. And the next place I see nickel where I could sub it out is about 5.3 angstroms, and then again at 6.1, which are out here. I'm not going to swap out any nickel for aluminum out here because I'm not going to fit out there, but you could if you wanted to. So now I've added swap deleted atoms. This is going to be down here. Okay. And we selected our R range. Now we need to select our path, label those variables, transfer them to guest def set list, and fit. So we got our FEFF input file all set. We're going to run FEFF. To calculate our scattering paths. And now that I'm thinking about it, I just want to go back and emphasize that Atoms is a program inside Artemis that uses your structural model to create your cluster. And all the atom locations in terms of XYZ coordinates within that structure, within that cluster. FEFF takes that list of atoms and calculates the scattering paths in terms of their contribution, their amplitude, and their phase. So now we have our list of atoms and the scattering path, and we're going to select our first shell, which is our oxygen shell, 1.65 plus about 0.4 is 2.05. This is our first one here, and you can see the degeneracy is a little bit different here. It's not 6. That's because there's a little bit of distortion in the octahedron. So I'm just going to pick one of these paths and assign them all to be 6, because that's what... Actually, I'm not going to assign them to be 6. What we're going to do is, because I don't have a standard for this sample, we're going to guess the coordination number for each shell. And the way to do that is using some math terms. We set the coordination number here to 1. We still use the amp term, but we're going to multiply it by coordination number of oxygen. Okay? So in our guest def set list, right click on amplitude. We're going to set the amplitude to 0.9. And we can account for the error in coordination number by doing this through a procedure that's outlined and well mentioned in the previous presentation. So we're going to set amplitude here to 0.9. We don't have a standard here to determine our amplitude reduction factor, so we're going to assume it's somewhere around 0.9, which is a likely assumption. We're going to guess, if you right click on this portion of the equation, we're going to guess our coordination number for oxygen, and I'm going to guess it's around 6 because we know it's I know it's an octahedral structure. E naught delta R for oxygen and sigma squared for oxygen. Guess, guess, guess. Fit. Okay. Visually, the fit looks good in terms of magnitude and phase. Our R factor is very low. Coordination number, the number that we guessed, is 6.17. So that's pretty close to 6. And we have this as an error, 0.2. So it's 6.17 plus or minus 0.2. But you also have to add in the error because I set the I also have to add in the error to the coordination number because I set this at 0.9. And there's a procedure to do that outlined in EXAFS for everyone, basically taking into account the assumption of this amplitude reduction factor being 0.9 if I assign it that value. So our coordination number is 6.17 plus or minus 0.2 plus or minus a little bit more because of my assumption here that amplitude reduction factor is set up is 0.9. E naught is reasonably low, delta R is reasonably small, sigma squared is pretty small as well. So the first shell fit looks good, and I'm going to go on to fit the second shell. I'm going to move my R range to about 3.2. All right. I'm going to take a quick break here from this sample to illustrate something before I forget to do that. It goes back to partial occupancy. So if you're loading a CIF file into Atoms and it has partial occupancy, you'll get an error. And so how do you fix that? Atoms doesn't do calculations. It doesn't do its cluster calculation if there's partial occupancy. So in order to fix that, you need to go into the CIF file itself and change it. All right. So for example, I was fitting a sample with this standard Enstatite. And so we'll go back and forth between the two. So here's the unmodified Enstatite CIF file, and here's the modified one. You can see it by up here, Enstatite or Enstatite _1. So here's Enstatite _1, Enstatite 1. If we look at the atoms list down here at the bottom, we can see the calcium and magnesium are in the same spot. But in terms of their site occupancy, 1, 2, 3, 4, 5 rows, atom label, X, Y, Z, site occupancy, these are at the same exact position. But 94%, 95% of the time it's a magnesium, 5% of the time it's a calcium. If you try and load this file into Atoms, which is in Artemis, you'll get an error. So what you do is you just you set the atom to an occupancy of 1. And I actually deleted the other atom because I wasn't interested in it. So you can see here the calcium is present. Here it's not. Here the magnesium had an occupancy of 0.948. Here it's set at 1. So this file you can load and run in Atoms. So that's an example of what to do if you have this partial occupancy problem. And if you're just starting with this program, you might run into that problem, and it actually becomes a significant roadblock if you don't know how to deal with it, especially when you're just first getting started. So anyway, apart from that digression, let's get back to finishing up this sample. And I was on, I think, moving out my R range. I moved it out, and I need to select scattering path. So at this second distance here, the second shell, 2.7 plus about 0.2 to 0.5, which is the phase shift, gives us a range of about 3. And we have a couple of options out here at about 3, including silicon, which is part of this second shell. And these are all single scattering paths. So the first thing I'm going to do is drag and drop nickel in, because I know nickel is the second neighbor here. This is nickel reacted with pyrophyllite. So we know that we're forming precipitates. I'm going to guess the coordination number here because I'm not sure what it is. And instead of manually typing in 3, 4, 3.4, 3.5, I'm going to go ahead and set this to 1, use my amplitude reduction factor, which is set at 0.9, and multiply it by a coordination number for nickel. Alright, so we know that's set, and we're going to guess. Let me open up my list. We're going to guess this. E0 is already up on our guess def set list. Delta R is for nickel. Sigma squared for nickel. So I'm going to guess these two and go ahead and do the fit. Visually, it looks good. In terms of magnitude and phase. So look at this, the R factor is really small. Our coordination number is guessed to be 4. Sigma square values are reasonable. So if I didn't know any more about this sample, I could call this fit done. But I do know more about this sample. I know that it's not just nickel in the second shell. And I know that because of this beat pattern here. And in the literature, it's been studied quite a bit. So I am going to go in and grab the aluminum and bring it in here and see what happens to the fit if I do add that as well. So I'm going to set that at 1, use my amp factor of 0.9, that's set. I'm going to grab the best ones. Call this coordination number for aluminum. Guess, fit. Now I'm adding quite a bit of free parameters here. I'm only in the second shell. I'm up to 12. The fit looks good visually. Let's see how it changed statistically. Our R factor with just nickel in the second shell and 7 variables was 0.0069. It went up a little bit actually by adding those 3 free parameters. So our fit really didn't get any better. But I know that aluminum is there. And I want to keep it in because I know physically it is located and chemically it's located in there. And the fit actually still looks pretty good with it in there. So it's saying our coordination number for nickel is 6, and for aluminum it's 3. Now there can only be 6 atoms in the second shell, so for this structure. So that's high. Well, that's a high value. Our sigma square value for aluminum is kind of low. It's a lighter element, and I would expect it to have a little bit larger sigma square, somewhere along the lines of this or higher. So I'm going to restrict, because even though they are different Z, they're different elements, but they're in the second shell, I am going to constrict them to being the same thing. So I'm going to set the aluminum one to be that as nickel. I'm going to skip it here. Go through and do the fit again. Gets a little worse. Okay. So our R factor went up a little bit, but we reduced one of our free parameters. Delta R for aluminum, delta R for nickel. So these two, our sigma squared is still reasonable for nickel, and this actually is both nickel and aluminum at this point. Coordination numbers are still high for nickel and aluminum. It should be less than 6 total. What else do I know about this sample? I know that aluminum and nickel are in the second shell and should be basically at the same position. So what I can do here is, even though this value and this value don't overlap, I'm gonna assign them to be the same, because I want them to be exactly the same distance in the second shell, because I know that's where they should be. So I'm then going to go ahead and set aluminum here to nickel and remove delta R aluminum. Guess. Skip. And fit. And actually, our fit, we went from 9 parameters and an R factor of 0.0018 to 0.0016. So our R factor goes up a bit. It's still well within the good fit range, and we also reduced one of our numbers of fitted parameters. Now actually what we're doing is we brought down this coordination number to a more reasonable value, because it was at 6 before and this was at 3. So that's total of 9 atoms in the second shell of the hydroxide sheet, which is 3 more than should be there. So those values are not physically reasonable, which is why I'm continuing to push this fit by adding different restraints. So what I did here is, now I force them to be at the same exact distance. And if I want to go in and see how those paths look, I can click this blue button, transfer those paths, and plot them. You can see that they're pretty much out of phase with each other, going up and down and up and down. So now we're getting them to cancel out a little bit more. So the more aluminum you add, the more it's going to cancel out the nickel, because the scattering waves are out of phase with each other. Okay. So what else can I do here? How else can I restrict this fit? Not in many other ways. I don't want to assume that the nickel and aluminum have the same coordination number, though we could try that to see what happens. What else do I think can be possible here? Well, I know that over time silica or silicon also dissolves from the phyllosilicate mineral, the pyrophyllite, and can form a tetrahedral sheet on adjacent to the hydroxide sheet of this sample of the layered double hydroxide. So if I go back into my FEFF list, I can select the silicon, and that's the distance of the tetrahedral sheet from the scattering central absorbing atom in the octahedral sheet, and it's still part of the second shell. So R effective is 3.29. Again, I'm going to guess the coordination number of the silicon. Call this amp times coordination number silicon. E naught is the same. Delta R nickel is the same. Silicon. Sigma squared silicon. So I can add these two free parameters to the fit. Use best. And we'll go ahead and fit and see what happens. I didn't guess it. There we go. Okay. So now the fit looks great here. Very visually it looks great. Our R factor dropped down again, but we increased the number of free parameters, fitted variables, to 11 by adding those the silicon shell. The values look reasonable also for the silicon shell. We can see the coordination number for nickel dropped even more, and the one for aluminum went up, which is good because now they're about 6. The error is a little bit large on here, which is what I would expect. There's a lot going on in this second shell. But these are more reasonable coordination numbers. And you can see if I plot them again, the aluminum amplitude is bigger and it's still out of phase with the nickel. I'm going to see how else can I restrict this fit. I'm getting penalized for using too many independent points. I also have a correlation above 0.95. Sigma squared and coordination number, those generally are one of the first ones to become correlated. As one gets smaller, the other can get smaller as well. So how can I restrict this fit, which is a way to break correlations and also reduce the number of independent points? So I see my sigma squared is at 0.007 plus or minus 0.005. That falls within the error range of the sigma squared for the second shell here, which is actually a little bit low. It's lower than the first one, so that's not ideal. But because they're part of the second shell, this silicon is part of the second shell, I'm going to restrict it also to share the same sigma square value as aluminum and nickel. So we're going to skip it down here. I'm going to guess I'm going to guess the coordination number. The delta R, because this is the tetrahedral sheet attached to the octahedral sheet, I'm going to assume any change in the octahedral sheet in terms of expansion or contraction or distortion is going to be similar to that and also influence that of the tetrahedral sheet. So I'm going to go ahead and set this delta R to nickel. So all of them are actually sharing the same delta R value. And just, I guess to clarify it, I could just call it delta R because it's not just delta R nickel. So I'm just going to call this delta R. So what did I do? I removed 2 free parameters. This should go down to 9 on the next fit. So hopefully I won't get this penalty anymore, reducing the number of independent points. And my correlation, hopefully I can break that correlation. So let's see. Go ahead and fit. Okay, I did not change. You skip. I'm basically trying to use this variable, but it didn't include it in the path list, so you get that error. Okay, you can see the color coding went more greenish. Let's see what the R factor went up a little bit. My number of independent data points went down to 9. We did break that correlation. It's down to 0.9. Our error on nickel went down quite a bit, which is good. The aluminum coordination number for aluminum and nickel look good, as does that for silicon. If we go down to the bottom, we can see what the determined values are. So we can see here the delta R value here is the same for all of them. It's bringing them in a little bit compared to the model at 3.05 and 3.05. So I told him these had to be the same. I assigned this value to be the same. So actually I think this fit looks pretty good. Chemically, it's got everything that I want in it, and the values are all physically reasonable. Coordination number. Remember, all of these coordination numbers use an amplitude reduction factor, which is fixed at 0.9. So it's going to be plus or minus this value plus an additional square root value that you'll have to calculate and add to that. But E naught looks good. Delta R is small here. Sigma squared looks good for this one and this shell. They're about the same, actually. Delta R is small here. So chemically and physically, I like this fit. It has everything that I want in it, because I think silicon would eventually, over 6 years, form as a tetrahedral layer on this sample. So what can I do to prove to myself that adding this aluminum and silicon really did improve the fit? Going through this series of 1, 2, 3, all the way down to 7 fits. So we started with just the oxygen shell, and then we moved to fitting the second shell as well with just nickel. And we can see the R factor is 0.0069 for that fit. And then we added aluminum and we restrained it a little bit, and Then we added, I think, another restraint to aluminum, and we added silicon, and then we restrained silicon. So here in this fit, chemically I'm happy with the coordination number and it with the elements, and physically I'm happy with the coordination numbers, and their errors are fine. But how do I know really if this fit, which has aluminum and silicon in addition to nickel, is actually better than the second fit, the simplest one with just nickel in it? So if we look at the R factors of 0.0069 for this fit, which has 7 fitted parameters, free parameters, or numbers of variables, and we look at this fit here with aluminum and silicon added, and we only have 9 fitted variables, fitted parameters, and our reduction factor goes down to 0.002. Is that really a significant improvement? I mean, they're both reasonable fits. They both have very acceptable R factors. So one way to determine if that's a significant decrease in R factor is to compare the two using the Hamilton test. If we look at the R factors for both of these fits, .00269, .0027. So we're plugging all these variables in here. 0.007 divided, or 0.0027 divided by 0.007 is 0.386. The degrees of freedom is 6.2 for the better fit. Divided by 2 is 3.1. And we added 2 free parameters, so 9 minus 7 is 2, divided by 2 is 1. And some of these values I changed, so don't pay attention to all these up here. So if we go into our calculator and put these values in, 3.1 for A, 1 for B, and 0.386, and we calculate, we get a value of 0.52, which is equal to 5.2%. Now, if we're using our 95% confidence interval, it's just outside that confidence interval. But I'm arguing that because we are chemically improving the fit by adding those atoms, and they're physically realistic distances, that I still think this improvement is significant. So I'm going to leave them in there. The R factor does drop quite a bit, but the Hamilton test shows it's just borderline 95% confidence interval. So there's a 5.2% chance the difference between these two fits would occur by random variation, or a 5.2% chance that the difference is just due to noise in the data. So you can play with the number of independent points. And actually, when I did this fit before, I think I used a little bit larger R range, and the Hamilton number dropped down to like 4.4. So really, at that point, you're just splitting hairs. So it's up to you to decide what's defendable or not in terms of the chemistry in your sample and the physically reasonable results. So if you can defend it, then you can probably do it. And if you have any questions about what is defensible, I suggest using the FEFF mailing list. So this concludes the fitting of those 3 samples and the second part of the workshop, where we highlighted this fitting protocol, which is designed to get you started on the fit, and then you get into the nitty-gritty after that. But for those just getting started using Artemis, this is the general sequence of steps you would take. So with that, I conclude the second part of this workshop.